Hi, this is lecture number 49 on subsurface drainage design. We are going to continue from the previous lectures. So, in this basically we are going to talk about the drainage base width or drainage base depth. So, that is very important because that decides the cost of excavation and finally the cost of drainage system, and then followed by the malfunctions once the drainage systems is installed and what kind of problems we are going to face and how to detect those problems and how to rectify those problems. And then the third aspect is like so drain pipe size design based on some thumb rules, and then so finally the disposing the drainage water and what kind of the possible ways to dispose and how we can use or reuse them. So, all these things we are going to describe in this lecture briefly. So, so the first thing is the field drainage base depth. So, this is, as I said, this is a very important thing in drainage system design for a given H. For example, for a given H, so the drainage, what is this? Okay. So, for a given H, so that means if you see this is the H. So, for increasing W, so W is the drainage base depth. So, if you can increase that, if in order to increase the W for keeping H as constant. So, small h is going to increase. So, and the small h is going to increase, then you need to arrange a wider drain spacing. Okay. So, the drain spacing has to be increased. So, and for the deeper drainage base could increase the cost of installation, because the moment if you are digging too much, that is increasing the W. So, that leads to installation cost increase, and so definitely due to the excavation cost. So, generally 2 to 2.5 meter these extra costs are normally compensated by the savings resulted from the wide spacing. So, as I said, so when W is increasing, so at the same time the spacing is increasing. Okay. But the thing is, in order to compensate the increasing depth that leads to the cost of excavation cost of this, and so since so that can be compensated by increasing the the spacing between the drains, so that you decrease the number of pipes. Okay. So, here in this graph is clearly showing, so W on x axis and cost benefit ratio on y axis. So, here as W is increasing like 2.5 and other. So, the cost benefit ratio is going to decline up to certain depth, then after that it slightly increases. Okay. So, here this is the critical depth, we can say this is the minimum depth where the cost benefit ratio cost to benefit ratio will be less. Okay. So, then so this similarly at the same time if you take the length on other axis, right. So, wide the length needs to be widen up, and if you can combine the W and length on other, and like for example, this is Z axis, x axis and y axis, and if you can draw a 3-dimensional view, you will be able to find out exactly where the W and L will have a minimum cost benefit ratio. Okay. So, then the next is the local conditions that influence the drainage base depth. So, what are the local conditions? So, one is the as I said I mean the spacing that we previously mentioned. In addition to that, the local conditions also influence the drainage base depth. For example, the drainage base, the local or regional drainage base. Okay. So, for example, rivers or the oceans or whatever may be. So, the field drainage base should be higher than the local drainage base. This is always recommended, because otherwise what happens, you need to pump water from the drainage to the sinks, okay, or the local drainage base. So, you need the extra pumping cost involved in that. So, always the field drainage base should be higher than the local drainage, so that the drain water will flow freely or flow by gravity to the drain base. Or the other one is soil conditions. So, the pipe should not be installed in quicksand, because that is really the pipe network is going to sink, right, and breakage is going to occur, it's completely the drainage system is going to fail. Then unconsolidated the soil condition, and the layers with low hydraulic conductivity. So, this is another thing we need to consider. So, if suppose the pipes are installed in the soils with low hydraulic conductivity. So, what happens, the water will not enter into the the drain pipes, and that will be the problem for the drainage. And drought risk. So, a deep drainage may over drain the soil. Pipe drain depth will mostly be based on the wet season situation. So, what happens if you design the drainage system based on the dry season situation? So, it will be installed in the deeper, right. So, what happens during dry seasons? So, the extra water will be drained out very fast, and the soil will be an unsaturated condition, and the water will not be available for the plant. So, that is why. So, here in order to avoid the drought risk, so the installation should be practiced during the wet season situation. So, that we know exactly where will be the water table. Okay. And the seepage. So, the local drainage base may constitute a sink drawing excessive amounts of seepage water from the surroundings. So, suppose if your drainage local drainage base is lower, right. So, this is your field drainage base, and this is your the local drainage base, right. So, what happens? So, because of this local drainage, so the excess water is going to seep to the field drainage base. So, this should be avoided. And available machinery. So, the most economical working depth is around 1 to 1.2 meter. So, this is the drainage depth. If you can go 1 to 1.2 meter, this is economical. So, if you still want to go deeper, then there are special machines are required. So, that will be really the costly. So, the next is the finding out the diameter of the pipe drain, right, pipe drainage. So, the drainage the hydraulic drainage for pipes, design of drain pipe using standard pipe flow formula, so like Hoogout equation, whatever it may be. So, basically these are the parameters we need to consider: the discharge, hydraulic gradient, and pipe diameter, and wall roughness. Okay. So, for example, for uniform flow, so the smooth pipes Darcy-Weisbach equation is preferred here. So, this is the preferred equation: Q is equal to 50 d power 2.71 I power 0.57, where the Q is the discharge along the pipe meter cube per second, and small d is the pipe internal diameter, and I is the hydraulic gradient, right. The units are given, whereas for corrugated pipe, the Chasian-Manning's equation, the Q is equal to 22 d power 2.67 I power 0.50. Okay. So, you have to remember this. So, if you look at this equation, so for corrugated pipe, the discharge is almost 50% lower, right. So, here 50 and 22, almost 50% less discharge you may expect in corrugated pipes, right, along the pipes. Okay. So, the next, this is for uniform flow, and similarly for non-uniform flow. So, you have as different equations. For example, here for smooth pipe, you have Q is equal to 89 d power 2.71 I power 0.57. Corrugated pipe, Q is equal to 38 d power 2.67 I power 0.50. So, these equations we can use. So, here for the uniform flow, so if this is the pipe, if this is the pipe tail pipe, so the hydraulic gradient line is exactly lying over the top of the water surface in the drain pipe. Okay. So, whereas for non-uniform flow, so if this is the pipe, right. So, you can observe this actual hydraulic gradient line. So, just a curvilinear, right, above the top of the water level in the pipe. Okay. So, where if h is if small h is the difference between the pressure heads, right, at this point and this point. Okay. So, here generally in case of non-uniform flow, so you may expect overpressure, that is maximum 0.4 h is expected in the actual hydraulic line compared to the average hydraulic line. So, here the average hydraulic line is, so this is the average hydraulic line. Okay. So, the point here is due to non-uniform flow, you may expect the hydraulic gradient line little bit higher than the average grade line. Okay. And here, so over design is practiced to increase the discharge 1.33 for stable soils and 2 times for siltation prone situations. So, considering the lifting and misalignment of the piping. So, you got the designed diameter of the pipe, right. In order to avoid certain situations, you may have to add some extra safety of factors. For example, for stable soils, you may have to multiply with 1.33 as a factor. So, factor is 1.33 to the design discharge, whereas for silt prone situations, you may have to multiply with 2 right, in order to avoid the situation of siltation. Okay. So, these extra design like over design needs to be considered in case of drainage, okay, drain pipe design. So, and the next is, for example, here if you see, so finding out the diameter of the pipe, the smooth concrete collector pipe, okay, and the slope of the pipeline is 0.1% and receiving water from 20 hectare of land drained by field drains designed for Q is equal to 5 mm per day. So, this is the discharge we are I mean the design discharge we are expecting small q, and allowance to be incorporated for subsequent 25% reduction in transfer capacity due to siltation. So, here at least, so after getting the design you need to consider 25% reduction in transfer capacity due to siltation. So, that you need to consider. So, you have to enhance the drain pipe size. For example, here the discharge at the end of the pipeline Q, capital Q is equal to small q into area divided by, you just conversion, this is unit conversion because Q is mm per day. So, just convert into meter cube per second. So, you get Q in meter cube per second okay. So, Q is equal to 0.0116 meter cube per second after substituting A and Q into the above equation and allowing for situation, right. So, the situation is mentioned 25% extra 25% reduction. So, 1 by 0.75. So, you get 0.0155 meter cube per second is the over designed So, now Q is equal to, so you have to consider the equation, right. This is the steady state, I mean uniform flow concrete pipe, smooth concrete pipe. So, you have to use 50 D 2.71 into I power 0.57. So, substituting small d and substituting for Q and substituting for Q and substituting for I, you get small d is equal to 22 centimeters. So, that is inner diameter. Okay. So, similarly, there is a second example here. So, this is for non-uniform flow. So, here the parallel system of pipe drains at 25 meter spacing. So, the pipes are installed 35 meter spacing. It is a corrugated plastic drain pipe and length is 200 meter and Q is 5 mm per day. This is a drainage flow and slope of the pipeline be 0.1 percentage. Okay. So, from here we know the equation Q is equal capital Q is equal small q into A by 1000, that is meter cube per day. So, substituting the area is 200 meter pipe length and 35 meter spacing. So, that will be 7000 meter square at small q is 5 mm per day. Okay. So, that in order to convert that you divided by 1000. So, that it will be in meters. So, now q is equal to 35 meter cube per day if you substituting all these things. So, now taking 50% of safety to allow for situation. So, 50% safety. So, 35 by 0.5. So, that will be 2 into 35 and 17 meter cube per day, or this is the design Q. So, now since this is a non-uniform flow, right, and corrugated pipe. So, we take the equation for corrugated pipe under non-uniform flow condition and substituting I and capital Q, you get D is equal to 64 mm. This is inner diameter. Okay. So, now, once the pipe network or the drainage system is installed, so you need to observe what kind of these kind of malfunctions you can look in. So, what are the checkpoints and what we need to check whether the system is working properly or not. So, here the overall functioning of the drainage system can be checked based on the water table observations on and also the individual drain discharges for basically for malfunctioning. So, here for that, so this is the drain pipe, right, and these are the piezometers, let us say 1, 2, 3, 4 and 5. Okay. So, the piezometer 5 is exactly installed in the drain pipe and 4 a distance of 10 to 20 centimeter from the the pipe drainage, right, just to know the just outside the envelope, okay, just outside the envelope. And third, in order to capture the water table, and second the local water table, and the first one is if there is any there is a vertical flows or something like that. So, so these observation wells are installed near to or exactly from the middle of or between the two drain points, okay, or two tail drain points. Okay. Now, so how to observe whether the system is working or not. So, there are 4 cases. So, case number 1, if you see for example, impeded infiltration or percolation. So, the infiltration water is not infiltrating down or not percolating inside the soil profile. So, in that case the evidence could be purged water table, right. Purged water table means, so there is a formation of the local water table, right. So, and because of the formation of the clay layer below the local below the soil surface or and water ponding on the surface because of that. So, evidence could be so here if you see the observation well number 1, you can clearly see the water present in the observation well number 1, whereas no water is present in well number 2. So, that means there is a purged water table which is causing the water which is staying here, right, the entire profile. So, that is purged water table, and because of this the water can stagnant on top of the surface. So, the causes could be hard clay pan here, right, this is a hard clay pan, and soil compaction. So, there is a lot of heavy trafficking might have happened, because of that the compaction could have been taken place. So, the next is case number 2, if you see, that is high resistance in groundwater flow, right. So, there is a lot of resistance and the water is not flowing as desired. So, in that case suppose the same thing all piezometers we considered in the previous case. So, evidence is slow fall in water table. So, water table here if you see the fall in water table is slow, right. So, if you observe one day and second day if you see still water table is not falling, but whereas the piezometer the water in the piezometer has exactly installed in the tail drain, there is a deplete in water level, but whereas the water level here and here is less. So, here depletion is not matching with the depletion of water taking place in piezometer 2 and 3. So, that indicates there is some problem in the the soil matrix. So, that means there is high resistance in groundwater flow. So, this could be under design. Okay. So, or overestimation of hydraulic conductivity while designing. So, you might have taken higher hydraulic conductivity. Okay. So, higher hydraulic conductivity definitely influences the spacing. So, the spacing might have increased. Okay. And drainage coefficient was underestimated. So, your K is low. Okay. So, if you bring Hoogout equation, once the K is low, right. So, definitely the Q will be less. So, and wrong drain spacing formula, you are using wrong drain spacing formula, like the parameters you might have missed out, right, in the equation. So, that may definitely influence the under design. Okay. So, the next case is high entry resistance. So, high entry resistance here if you see at this point we are expecting this is what envelope, right, envelope. So, here so water is present this outside the envelope, there is a lot of water, water is really accumulating here, which is not entering into the pipe, entering into the envelope, right. So, that is really causing the high entry resistance here, high entry resistance. So, common causes of malfunctioning, this is the main common cause of malfunctioning. So, that is why envelope material really needs to be designed very well, and drains have been installed in a trench by unsuitable methods, and other could be like while installing the drains the methods are not suitable, maybe unsuitable methods might have adopted to install the or laying the pipes, and omitting the envelope. Sometimes if you omit the envelope, that definitely going to clog the pores. Okay. So, in this case no solution, only you have to redesign the pipes. So, you have to redesign the entire drain system here. And the fourth cause or fourth case could be obstructed pipe flow. So, the pipe flow is obstructed. If you see here like observation 5 and 4, right, observation 5 and 4. So, the flow is obstructed. So, that means the water here this is, if you see here the water level is almost at the ground level, right, at the ground level. So, we expect the same thing here, because once this is ponding, this is we are expecting the ponding is taking place here. Okay. So, but in this case what happens, because the too high water level in the collector ditch, right, too high water level, these are the observations. So, you may observe sometimes too high water level. So, here if you see, right, there is a lot of pressure, it is happening, right, it is supposed to be here water, but it is coming all the way up to the here, that means a lot of pressure is taking place, and too small pipe diameters, that may happen because the too small pipe diameters, the excess water is rushing, right, filling up the observation well, and misalignment of pipes, sometimes misalignment of pipes also pressurizes the flow, and clogging of the pipes by fine iron compounds. Suppose clogging of the pipes will reduce the open areas, and that really influences the obstructed flow, and blockage of pores by roots. So, this since we are designing for agricultural drainage. So, there is a root intrusion might have taken place, and that when the roots may enter inside the pipes, and that may clog the opening, and that reduces the open area in the tail drains. Okay, so then the next is the drainage environmental consideration. So, once the drain flow is out or once the drainage water is coming out. So, how to tackle that water in terms of the environmental health. Okay. So, environmental consideration, if you see, the drainage has an impact on the environment. So, because of that, and this is under scrutiny by regulators and environmentalists. So, because the drainage water consists of, because the drainage water is coming from the agricultural lands. So, definitely it contains a lot of nutrients. Okay. So, that is not undesirable. So, that is, of course, that is undesirable for the local water bodies, because the moment the drainage water, which consists of high nutrients such as nitrates and the phosphates. So, definitely that will be the food for aquatic plants. So, for example, algae. So, that definitely is going to grow in the local water bodies, and then that causes the environmental or fish killing and other things, okay, toxic to the aquatic animals. So, of course, the drainage water normally carries high nitrate load, of course, the phosphate loads also, potassium. So, Fossil and Belcher 1991, they listed the following positive environmental impacts subsurface drainage. So, these could be negative, because that is really causing the eutrophication in case of the nearest water bodies, but whereas there are some positive environmental influence like reduced overland flow and erosion. So, the moment the accumulated water which is percolating down into the soil, so that means the overland flow is going to reduce, and definitely that is going to reduce the erosion and reduce the sediment transport. Of course, this is the same thing. So, once the ponding water which is once the runoff is reduced, definitely the sediment transport and attached phosphorus and potassium of the form are going to reduce, because the phosphorus potassium. So, they will be retaining on the top layer, right. You can say the active layer of the soil, that will be like around 5 to 10 mm. So, that is very important. Suppose if that soil is not washing off from the fields, and definitely you are going to cut off the phosphorus and potassium loads into the local water bodies, and improved surface nutrient management. Since the nutrients are not running off from the fields, definitely you are going to retain the nutrients on the field, and you can improve this surface nutrient management, and improve the ability to monitor percolating the flow. So, because so these drains are going to create the negative pressure. So, definitely that will improve the percolation of water, and reduction in the non-point source pollution. Ultimately, the non-point source pollution or diffused pollution. So, that is going to decrease due to the drainage systems. Okay, so, and then the drainage environmental considerations. So, NRCS, that is Natural Resources Conservation Services, recommended several techniques for the reduction of impact of drainage rainwater on the environment. So, as I said, the nutrient load is going to be the drainage water which is coming out from the field. So, that is going to influence negatively on the water bodies. So, NRCS has recommended several techniques how to reduce that, and install on-farm detention ponds or wetlands that reduce the nitrogen concentration drainage water before leaves the farm. So, once the water is drained from the fields. So, here if you have the wetlands or detention ponds, so the drainage water is going to accumulated here, stagnant for some time, and all nutrients are going to settle down, and then if you want to reuse this water, you can very well reuse it. And retrofit drainage systems to reduce drainage during critical periods and manage the water table. So, sometimes what happens, so you may have to construct a wall right. Suppose here is the drainage, here is the drainage. In critical cases, what happens? So, the over drainage needs to be stopped. So, this wall will not allow the excess water which is which may not be going. So, water will, so the wall will protect water to be seep from one place to another place. So that here you can still manage the water table, okay, for a desired, under a desired drainage discharge. Okay. So, this definitely the retrofit drainage systems. So, the another example is, suppose in that case you have here the outlet, for example, right. So, let's say there is a gate, the complete drainage line. Okay. So, drainage water is going to enter into this chamber, right. So, you can maintain the water table, you can maintain the water table. So, based on the opening and closing of this gate. Okay. So, if the gate opening up to this level, right. So, entire water will be used from here and opens. So, you can maintain the water table up to this. So, suppose if you want to maintain water table up to this level, so up to this. So, only opening closing of the gates can help in monitoring or managing the water table. So, implement cropping systems that reduce nitrate losses. So, other option could be you can also implement the cropping systems, so that reduces the nitrogen losses and improve fertilizer and animal manure management timing. So, these also, like you also improve the fertilizer and manure management timing. So, suppose in winter if you apply a lot of fertilizer before the frost event or freezing conditions. So, what happened during summer? So, all the manure which is spread on the ground will be transported to the nearest water bodies, right, because of the snow melt. So, the annual manure management also very important in case of the drainage. Okay. So, the drain discharge management. So, disposal could be so the options for disposal agricultural drainage, return the water either to natural depressions or lakes or rivers, or to salt sinks such as oceans. So, here either you can dispose it to the nearest water bodies or the oceans, right. So, if the suppose return the water either to the land or part of the irrigation water supply. So, in the two ways, one either disposable like the water bodies or the oceans, the other you can dispose the water to a pond or wetland, then from there you can reuse for agricultural purposes. If you see this, so the drainage water which is coming from the field is being pumped to the local water body here, and the same water can be pumped back to the sprinklers, right, for irrigating the fields. This is one. And constructing disposable basins or disposal basins for saline agricultural drainage waters. So, suppose if the oceans and inland closed basins are not the options, suppose there is a restriction, like you should not dispose the drainage water to the oceans or some other disposable lands. So, in that case, so you are going to constructing the disposable basins, you need to construct the disposable basins in nearest places. Okay. So, and finally, the treatment of drainage water. So, there could be like physical, chemical, biological treatments. So, these physical treatments are removing suspended solids. So, this is through sedimentation or flotation, centrifugation or filtration. So, and the filtration further includes granular media beds, vacuum filters, belt presses and filter presses. All these things are going to used in case of filtration process to remove the suspended solids from the disposable disposed water or drainage water. And so, other one is adsorption. This is a chemical treatment. See, adsorption is the process of removing soluble contaminants by attachment to a solid. So, for example, here removal of soluble organic compounds via adsorption onto granular activated carbon. So, the activated carbon, it has a particular charge and it is going to attract the opposite charge, the sediments or particulates or organic matter to the activated carbon, and then you can remove, separate the organic material from the drainage water by adsorption. And there is a distillation. So, the distillation is a thermal process used to salt removal. So, what happens, the the water which is drained from the fields will be stored in a ponds, and then due to evaporation the all water is fresh water is going to evaporate and the salts will be retained in the pond, and so generally heat or vaporized water leaving the salts behind. Then the salts can be scraped out, right, it can be removed from the ponds. Okay, so this is all in this lecture. So, in this we focused on basically how the drainage base depth. So, that is the importance of drainage base depth and what economical depth we need to go, right, and once the and also drainage the pipe size determination, and how to observe the malfunctions in a drainage system. We mentioned about the 4 cases. So, and then the drainage water disposal and how to reuse that and what kind of treatments we need to carry before in treating the drainage water in order to avoid any environmental contamination. Okay, thank you so much.